Buzzwords. Just to give you a bit of my background, I had my undergraduate education at the University of Virginia. I studied North African linguistics. My languages of focus were Modern Standard Arabic, Tunisian Arabic, and French. And then I had the weirdest career change of all time, and I got my graduate degree in astrophysics from Wesleyan University. So later, if you want to ask me questions about space, I love talking about it. My research there was on supermassive black holes and active galactic nuclei. And now I'm a data scientist for Booz, and I do a lot of things. A lot of my projects involve cybersecurity, but my real passion is ethical AI for humanitarian aid. The first buzzword, you wouldn't think it's a buzzword, it's data. And as I was conceptualizing this talk, I went around to a lot of friends, family, who aren't technical people, and I asked them, what's data? What does data mean to you? And I realized that this is a buzzword even if we don't realize it, because there's a lot of misconceptions about what data is. So anytime that you hear the word data, I want you to substitute information. That's all it is. I mean, there's good information, there's bad information, there's good information formats, there's useful information, but data by itself is just information. And the circle that I have up here is what, in my experience, has been kind of the life cycle of dealing with data. And so if you Google data life cycle, you'll get 50 different versions of this. But in my experience, these are kind of like the key components of using data, gathering it. So to start out with, you have to collect it or create it. You have to get your information from somewhere. And so this might look completely different based on what industry you're in. In my background, we point our telescopes at space and we get our data. This might look like customer satisfaction polls or financial spreadsheets, or it could just be information that doesn't have any labels, that's a lot of numbers. So whatever data looks like, if you're using information in your day-to-day business, and I guarantee you everybody in this room is, then you're using data already. The next step, once you've gotten your data, is to clean it. And this is my least favorite step. I worked for a while on an astrophysics project where the data just came in gaps, misspellings, dropped numbers, different data formats, and it was a nightmare. And I never, ever, ever want to deal with data cleaning again. I have to, but if I can delegate that, I tend to, because cleaning is a really arduous task, but it's necessary. Because once you have that information, if there are missing values, or if there are misspellings, or if it's coming to you in a format that you can't use with your software, you have to do something about that. You need that information to be in a format that is helpful and can actually be readily accessed. And then you get to the fun part, in my personal opinion, which is using the data or analyzing it. And so this is, I think, the best part, in my completely biased opinion. And this is where you can extract what we would call analytics. But really all that is you're deducing or you're inferring things from that information. And so we'll talk about what a data-driven decision is later. But in this step, it's really about looking at a big picture and looking at that information and asking yourself what it tells you. And a lot of times this can be a really tricky step. You would think there's this misconception about data that it's objective. And in a sense, it is, but when you're trying to get information from this big picture, a lot of times your own beliefs and your own ideas about what it might say or what it should say, or what kind of data where your source that you've gotten your information from, all of that can influence you in ways that are often difficult to identify. And then to me, again, another boring step, but if there are any data architects in the room, I'm sorry. And that's storing and preserving your data. This is absolutely crucial, but how we store our data, where we store it. I mean, for those of you who can remember, well, most of you probably can, but I'm young, but floppy disks. We've moved on to much better data storage methods now. VHSs, we've moved on, thankfully, to more effective ways of storing data. And so it's not just about using the most effective way, but for your business, you might be concerned about cost. You might be concerned about physical space. If you don't have the space to put the devices that you need to process that data, that can be an issue. But also you want to preserve it. You don't want to lose any of that data that you've worked so hard at this point to collect and scrub and get information from. And so even though I did joke and say this is boring, but actually it's incredibly complex and it's very difficult because you want to be able to go back and use that information later. So how you store it and how you preserve it is actually a very critical component. And then there's the step delete. And so a lot of times if you do the Google, delete and communicate are left off the data lifecycle, and that drives me up the wall because sometimes the most critical question is what data you don't want to use. And so if you have, say, a database of information about customer buying patterns, if they're from 50 years ago, they might not be relevant to you today, and including them in your decision-making process might actually lead you down the wrong path. And so knowing when to let data go, knowing when to delete it or remove it from your database is a really important step. And sometimes it's less fun than that. It's about the fact that you have limited funds, you have limited space, and you have to make a judgment call about what data to keep and what data to delete. And that's where it gets even trickier. And then to me, honestly, other than the analyze step, I honestly think that the communicate step is probably the most important. And that's one of the reasons I'm here today, is that this is where a lot of the trouble comes from, is that it's one thing to be able to sit down at your computer and be a more technical person and understand the data and run your programs on it, store it effectively. It's an entirely different thing to communicate what that information says in a factual, unbiased, and effective way to policymakers, decision makers, executives. And so it's really tricky because you have to strike this balance between having enough technical information in there so that people trust you and they see you that you are the expert. But then you also need to not overwhelm them with jargon. And coming from academia, that's one that I've seen a lot, is that a lot of very talented, intelligent academics stand up in front of a room of the public and they just start throwing out jargon. And they put up a bunch of equations, which for me might be exciting, but for most people probably isn't. And you lose people. And so knowing how to communicate in a way that people understand, using language that they understand without miscommunicating or without leaving anything out or without letting your own biases kind of push people in one direction. It's a really difficult thing, but I honestly think it's one of the most important things when dealing with data. And then like I mentioned earlier, talking about data-driven decisions. So this is another buzzword, and it kind of makes me laugh because on the one hand, I love that we're moving towards a business practice where we want to use information correctly and we want to use it well. But on the other hand, everybody makes data-driven decisions. Everybody. We make them every day. And so a lot of times when you're thinking about maybe the old way of doing things, where I'm thinking of like an old-time salesman who he doesn't have any Excel spreadsheets, but he just knows his clients. Well, actually, what he's got in his head is data. He has that information. He's thinking about it. It's just not written in a format that we would think of as data. So I have some personal examples. If you're, this is one that might not apply in Northern Virginia, but if you look outside and for the last 3 days it's been sunny and 65, I wish, you might say, oh, tomorrow's probably going to be much of the same. Again, unless you live in Northern Virginia, then it's probably snowing. But you might make decisions based on that. What you've done is you've taken data, your observations of the temperature, the sunniness, and you've inferred something. You've guessed, you've predicted what today will be, and that's a data-driven decision. Similarly, if you're picking what to wear, you might factor in what we might think of as unchanging data, like maybe your style or what your favorite color is, along with data that might change day to day, like the weather or what function you need to go to, or who you're meeting with. And so that kind of changing data combined with immutable data allows you to make a decision about what to wear. And other examples, especially when purchasing, you might have to compare, like take the example of buying laptops. Your number one ideal might be you want something that you can afford, but a lot of times more goes into it than that. So you might be thinking price, but you also might be thinking the operating system or how much hard drive space, or how much RAM. And all of those different characteristics are weighted differently. And that's a term that we'll come back to later, but think of it just as your priorities. Your number one priority might be price, but the operating system might be almost as important to you, so you're kind of willing to compromise. And so that's a really great example of a data-driven decision that feeds perfectly into when we're talking about machine learning later. Because that idea of combining information with weights to get an outcome is a really critical one. And then I had choosing holiday presents for a family, which can always be really difficult. But that, you might combine, again, all of that different weighting with what we talked about earlier with the immutable data and the changing data. So you might know, what your sister already owns. That's your immutable data, that's not going to change. But her hobbies might have changed this year, and so that's changing data. And then on top of that, you might have the price, the object, how much it means to her, all as different priorities or weights. And that allows you to make your decision. But in all of these, none of us would write any of this down really. We might make a gift list, but you're not going to sit here and make a table and a spreadsheet, make some graphs about what you should buy your sister for Christmas. But when we're scaling this up to a business, we need to take that same intuition of using information in an effective way, using different kinds of information to make a decision, and we need to add some things. We need to add scale, because it's one thing to make a decision about between 5 laptops, but when we're talking about millions of products, it gets a lot more complicated, and your brain just can't handle balancing all of those different data points. Similarly, you might have to increase the speed. It takes me a really long time to pick gifts for people, and I'm really bad at it, but if a business was in the market of making customer recommendations, they want to do that quickly, and they want to do it effectively. And you also want reliability. If you think back to the example of looking outside and trying to guess what the weather is, the consequence if I'm wrong is like maybe I'm too warm or I'm too cold or I don't have an umbrella. But for an entire business, it could be revenue lost. It could be customers lost. It could be making investments that don't have a good return. And so you need a reliability when you're scaling this approach of using information to make decisions. You also need accountability. And this definitely happens when we consider the fact that businesses are more than just one person. It's one thing if it's just me making the choice, but if you have teams of employees, you need some kind of accountability for how that information is being used and why it's being used. And similarly, you need reproducibility. It's one thing if all of this is in my head about how to pick, the best laptop, but until I can put that on paper in a way that somebody standing next to me can use effectively, it's not going to be helpful at the business scale. And so there are business use cases just like there's personal ones. So when we add those scale, speed, reliability, you get cases like Google used, it was Google or Amazon? Google, I think. They used data collection. So what they did was they had employee surveys about what people thought about their managers. Were they effective? Did they like them? Did they feel like their team had cohesion? And they compared that data with the team's success metrics, whatever those looked like, whether they're sales or whatever. And what they found was, and this might be obvious to us, but it's great to have the data to back it up, is that teams that rated their managers more effectively, the team performed better. And so then they were able to track different training programs, as I mentioned at the end, or different management styles to see what was the most effective, what actually influenced their team's performance. And by using reproducibility and scale and writing things down and having this in a way that is accountable, they were able to make better decisions on management and hiring over time. We also see these things with client recommendations, like I mentioned earlier, and then also predicting spending and investing trends. And there are a million different use cases, and this is why data-driven decision-making and big data and data science are becoming such hot topics, is because there are innumerable use cases, because everybody uses information to make decisions. But we're starting to question the best way to do it and how to make it reliable and how to scale it to the size of our business. And so that's really what the buzzword of data-driven decision-making is about, is that it's about taking this kind of intuitive process we all have about using the information at our disposal to make a decision and scaling it to the size of a business. And so as I mentioned, big data. This is another one that just makes me laugh, because what's big data? I mean, there's a Wikipedia article on it, there's articles all over the place, and what is it? It's big data. Like, the naming, I mean, so if you aren't familiar, in astronomy we have a bit of a bad reputation in the sciences for being horrible at naming things. Well, horrible or awesome, depends on who you ask. But there's the Very Large Telescope that I got to work with, the VLT. And when proposing the next, biggest, most wonderful telescope that we want to, get funding for, we came up with the Extra Large Telescope, or the Extremely, Extremely Large Telescope, ELT. And there's a very large array, and it's just like, it's kind of a field-wide joke. But this seems very in line with astronomy naming, is that it just is big data. It's a lot of information. But to kind of break it down a little bit more, big can mean two different things. It can mean size, so we're talking about the volume of your data. How many, if you think to the Excel spreadsheet, which I would encourage you to move away from, but it's a good visualization, that's how many rows you have, maybe how many sheets you have, how big that file size is. That's your volume. But then there's also complexity, and this is one that becomes incredibly tricky when we add machine learning into the mix. This is how many columns, how many characteristics or traits or features of a particular data point that you're interested in. So if you're talking about customer buying patterns, it could be anything from their historical buying patterns to what business they work for, their age, their preferences, all kinds of things like that. Those are all those traits that you'd be interested in when making a decision. And the more of them that you have, maybe the more nuanced you might think, or more accurate your decision could be. The more information, you always want more information, but that's where things get really tricky, because that's what introduces error. It's also what introduces a kind of complexity that can become really tricky for computers. And so you would think that you want your data to be complex, but actually it's tricky. And in particular, data can be complex in a couple of different ways. So there's variety. And anybody who's heard of multi-intelligence fusion or multi-data fusion, this is all about variety. And so that's, I have my imagery, I have my sound data, I have some text data, I have some numbers, and all of this is in different formats, and sometimes even the programs are written in different languages, and you have to get all of that into one place that's cohesive, homogeneous, that you can use. And so when you have complex data, sometimes it's all about the variety. And this can be particularly an issue like in astronomy, where you can have different wavelengths, and you can have information from different telescopes, and all of that you want to use in your research, but you need to get it to talk to each other. You need to be able to get it all into one place so that you can look at it all in a uniform format. And then there's velocity. And this is a big one in cybersecurity, and that's that the speed that you get your data. So this is where maybe astronomy is the best example, because you kind of gather your data, you got your data in a package, and use it. But in cybersecurity, events are happening constantly, rapidly. And the trick is we want to use that data, we want to use that information about the events to maybe identify hostile intrusion or to flag anomalies on a network. But the data is just coming in so fast that, one, we very quickly run into a volume problem, but also there's a velocity problem. How do we use data that's just coming in incredibly quickly? And then there's veracity. And this is what I was getting at earlier with the data cleaning, is that you can have missing fields, and you can have misspellings, and you can have data that maybe you don't trust. I mean, this is something, again, that I run into a lot in cybersecurity, where I want to compare the anomalousness, if you will, of two events, but I have 7 out of 10 characteristics for this one, and 5 out of 10 different characteristics for this other one. And how do I compare them? It's not always as clear cut. So when you have complex data, as great as it sounds, a lot of times it introduces even more problems. And I want you to think back to kind of that data life cycle, because these issues of size and complexity run across this entire cycle. Collecting it, just like I mentioned with the cybersecurity data, and also sometimes with astronomy, is that it's a lot of data. If it's fast, if it's really in a bunch of different formats, collecting it can be really tricky. Cleaning it, I don't think I need to touch on that one again. It's awful, it's messy, it's really difficult. Analyzing it, how do you, like I mentioned, how do you compare data when you might have missing features, or you have an incomplete picture, or maybe you're not quite sure that it is what it is. In astronomy, we have an issue with cosmic rays, that or missing pixels in an image. And if you don't know what you're looking for, it can look like a star, or it can look like, for me, unfortunately, it can look like a black hole, and you get really excited until you realize that you can't trust your data. It looks like something, but it actually isn't what you think it is. And then storing it, I think that's a really big problem for both volume and velocity, is how do we store that much data? How do we store it quickly? Deleting can be an issue, and this is one that also comes up in a lot of my cybersecurity work, that as all this new data is coming in really fast, we very quickly hit a size limit, and we need to determine what are we going to let go, what are we going to delete, what are we going to not use in making our decision. And that's a really, really tricky question, because more data is flooding in every second. And then communicating. Again, incredibly important, but very difficult. When you have very complex data, if you have something that has 100 features, 100 columns in your Excel spreadsheet, and you're trying to compare these things and you're trying to communicate the differences to an audience without sitting there and putting a bunch of equations on a board and losing them, how do you do it? You always have to make decisions about what to summarize. And in a sense, that's what you leave out. How much complexity are you going to leave out? And that's really difficult, because that's where you get into the problem of miscommunication. Anytime you're losing data, there's a risk that you're going to be communicating the wrong thing. And so this kind of brings me to what is data science. And it's a relatively new field. I think if you Google what is data science, you're going to get lists of tools and techniques that data scientists use. And you're going to get 50 different lists of 50 different things from 50 different people. And so there isn't always a consensus on what actually data science is or what a data scientist does. But these are a couple of the common ones. So things like computer science, data visualization, programming, statistics, these are all really useful tools. And there's a lot more, but I listed the ones that, at least in my experience, have been the most common. And then there's always the question of, what does a data scientist do? I get asked that a lot, what do you actually do? And it's, at least in consulting, it's what a service that you can provide. What can I give to a business to help them make better decisions? And so that might look like prediction, scoring things, optimizing workflows or optimizing procedures, detecting anomalies or patterns, recognizing objects or patterns in an image, or classifying things. And data science it's tricky, and this is my personal subjective opinion, but with the rise of things like data science bachelor's programs or data science, I think data science certificates and sometimes masters are a really good way to go, but I worry because one of the best things that a data scientist brings to the table is their subject matter expertise. So for me, that's things like astronomy. But on my team that's handling cybersecurity issues, we have a statistician, we have a mathematician, we have a couple computer science people, I think there's somebody who did bioinformatics, and we all bring a different approach. So you might think, okay, what does astronomy and cybersecurity have to do with each other? But the problems are actually very similar. Trying to find really rare anomalous events, or trying to deal with very low signal and a lot of noise. And sometimes my gut intuition about how to solve a problem comes entirely from my astronomy background, even though it's in a completely different field. And so I worry that people are misunderstanding what data science is. It's not just this checklist. You can't just go online and you print your thing and I know Hadoop, I know Spark, I know Tableau, I know SQL. That's great. Those are tools. But data science is about how to use them, when to use them, how to use them effectively. And that's the really tricky thing. Because anybody can learn the tools, and that's really fun, but knowing how to use them and when to use them is way, way more difficult. And then we kind of get to the fun part, right? As you saw in the previous slide, one part of data science that's often used is machine learning and AI. And this is another branch where there are a lot of misunderstandings. I can't tell you how many times I've talked to people about AI that I'm working on, and they, Skynet, and oh, it's a robot, and is it going to make toast for you? And I'm just okay, guys, it's just it's code. It's not as cool as you think. I mean, it's cool to me, but it's not this flashy, robot that's helping me out with my housework or something. But you might hear artificial intelligence used in two ways. One is as a branch of computer science. And so this is a branch that deals with machine intelligence. So if you hear people say I work in artificial intelligence, or I'm studying artificial intelligence. This is what they're talking about, the branch, the field of study. And then also you might hear people talk about AI or artificial intelligence as something they've built or something that they're selling. And then they're talking about, roughly speaking, a computer that can do things that normally we would expect a human to do. Decision making, identifying objects in an image, maybe being able to parse text and infer meaning. So those are things that normally we would associate with human intelligence, but if we can train a computer to do it, we've stepped into the realm of AI. Within AI, a portion of it is machine learning. And so machine learning and AI are not synonymous. And a good example of this is that I can write an AI to play checkers. And I can give it an exhaustive if-then list. If this situation, do this thing. If this other situation, I mean, do this thing. If this happens, then do this. And it's exhaustive, and it's enormous. But if I deploy that, my AI can probably play checkers well. But what it can't do is it can't get better at checkers, because all I've done is given it rules. It doesn't know how to take the experience and get better at playing checkers. If it can, that's machine learning. And so that's where you've written a program that gets better with experience. And so something that, I think one of the classic examples when you're first learning about machine learning is taking data sets, like I think there's one with tumors. And it's like size of tumor and like, it's like size and location. And training, based on that, you've got a big database of like size, location, and if it's benign or malicious. And you're able to, by using that data, teach a computer program to then identify tumors as malicious or benign that you don't know. You don't know if they're malicious or benign. And so that's a case of machine learning, where the more information that you give this program, the more that it learns, the better it is. And then at this very last minute, because I was thinking about more buzzwords that are kind of on the rise, and a big one is deep learning. And so this is, again, we're stepping within machine learning into neural nets. And this literally, I think of the people who named big data, named deep learning, they call it big AI, because that's pretty much what it is it's big neural networks. And so when you hear about deep learning and deep fakes, and we'll talk a bit about that in a moment, all that that's talking about is a large neural network. And so I love machine learning, I love AI, but it fails, and it fails a lot. And I think in some ways it's because of the issues of communication that we've talked about, but also it's because sometimes your data's bad. And a really good example of this is another cybersecurity example, but a team actually, I think, yeah, they were working out of the firm, and they partnered with Microsoft. They got all this great network data from Microsoft, and they trained their machine learning algorithm to detect what they thought were anomalous events based on all this Microsoft data. And when they deployed it in the field, they realized that they hadn't trained it to do that. They had trained it to identify problems in Microsoft. And so they were introducing this bias into their data without even knowing it by only gathering from one source. And then there's also issues with, like we talked about earlier, volume and complexity. The more complex your data, sometimes certain machine learning approaches will fail. And sometimes if your data is too simple, the same thing will happen. If you don't have enough of it. And I swear, I didn't realize this, but when I was very spoiled in astronomy, because if we do need more data, it's a little more straightforward to get. You know, you point your telescope where you want to look, for the most part, and I can get more. Most of my job is going to people and saying, please give me more data. I need more data. Like I could almost substitute like a cardboard cutout with like that recording, because that's a lot of my job is going to the clients being like, please, I need more data for what you want to do. Because in order to make these decisions and in order to train and teach a computer, you need a lot of data and you need really comprehensive data. And then there's bad implementation. And this is one that, for none of these I have like a complete solution. And implementation is a really big one. Because it's great to be, you know, a nerd in a room with other nerds and build this cool machine learning thing. It's an entirely different thing to see that used in the field by a business or, you know, by soldiers in the field or something. And how it's actually used effectively and made into a tool that people can use and understand is way harder. it's like the easy part, honestly, is what I do, which is just to create it. But it's way harder to package it and to design it in a way that is effectively implemented. And then there's ethics. And this is kind of a serious note to end on, but this is something that's really critical and it's becoming more and more important as AI gets better. So many of you have probably heard about deepfakes. And so, you know, the academic in me, the scientist says, this is so cool. We've built this amazing thing. We can do something that we weren't able to do before. But then the other side of the equation is, should we? Should we do that? Because now, you know, I think it's OpenAI has built a program that can generate pretty much indistinguishable news articles. And it's completely bogus, but it looks sourced, it looks reputable, there's images. It isn't, you know, like it isn't like Google Translate, which sometimes, you know, has those awkward translations. It reads fluidly, it reads like a real news article. And so, as cool as that is from the scientific perspective of, hey, we accomplished this new thing, we did this new thing, the question is still, should we? Or how do we do it so it doesn't get used badly? And then there's this issue in the industry also of black boxes. And I'm not talking about the ones on planes, but this is what we use to refer to an approach where if I built a machine learning capability for a client, and I said, okay, you're gonna give it, let me think, all of your network data, and it's gonna tell you how you should upgrade your network security. I'm like, well, how? I'm like, just trust me. Like, it works. Like, it's great, it's an algorithm, I'll throw a bunch of buzzwords at you, and it works. That's a black box. They can't open that up and see what's going on inside. They don't understand. And so for AI to be really effective, it needs to be explainable, and it needs to be transparent. If you're giving AI to somebody, if you're giving a tool to somebody, they need to understand exactly what their data is being used for and how. And then we talked about this earlier about the biases that we transfer into our AI and machine learning. And a really good example of this is the company that built the automatic hand dryers, that they only tested them on lighter skin, and so they ran into a problem where, like, darker skinned people, it wouldn't recognize that, and it wouldn't give them a paper towel. And so, I mean, that's one, it's bad business practice. Yeah, but also it's kind of like, you know, what biases are we introducing into our data, even inadvertently? And I think same with the bad data. One of the solutions here is to sample a wide distribution. And what that means is gather data from a bunch of different sources. And I also mean, though, not just gathering data, who you have working on the data. Get a bunch of different people, different backgrounds, you know, different approaches, because then you can hopefully avoid the biases of an echo chamber and make really ineffective hand dryers. It's just, that one really cracks me up. And then there's what are the consequences? And a lot of my colleagues work in defense, and so this is particularly a crucial question for them. But when we start to get into more controversial AI, you have to ask yourself, you know, one, every AI has error, nothing is 100%. So what happens when it makes an error? What happens if it fails? What are the consequences? For me, you know, in just like making decisions about the weather, right? Like I said, it's just, oops, I forgot my umbrella. But when you're talking about militarization, you're talking about lives lost. When I'm working in humanitarian aid, I'm talking about lives lost or lives in peril, and I'm sending resources in the wrong direction, or I'm putting resources into things that, you know, aren't going to be effective. And so the consequences is something that you should always keep in mind. Even if you're not the one building it, if you're the one asking, you know, I want, you know, machine learning to be brought into my organization, you have to understand there's always going to be a failure. And so what do you do if it fails? How do you maybe mitigate that failure? How do you mitigate your risk? These are really critical questions in ethics, and they're ones that I don't think are often talked about because AI is so shiny and new and wonderful. It's actually not that new, but it's new to the news cycle. And so we want the next greatest, shiniest toy. And I get that. Like, I play video games. Like, it's really bad, the money that I just sink into the next console or like the next piece of hardware. But with this, we have to pause and we have to ask ourselves if we should actually use it in the first place. Is it going to work? You know, there's plenty of cases where AI is not the right move. machine learning is not the right way to solve your problem. But also, when you're working in maybe more controversial industries, you have to ask yourself about whether or not it's right. And that's a way more difficult question. But I know that's like a really somber note to end on, so I included a picture of my dog. And I'll take questions about data science, questions about space, whatever you like. But this is my dog Hubble, so hopefully he'll lighten the mood after talking about militarized AI. But thank you.
Any questions? Okay.
Yeah.
Yeah, hi.
Hi.
One of the things that we've dealt with in our firm is who owns the data. Yeah, and because we had projects with the federal government, so if we're doing, if we have projects with a certain population, and so if the government owns the data, or those of us that are, our private company owns the data, or actually the beneficiaries, the persons, the population with whom the data is constructed. Do you have any thoughts about working in that kind of a realm of how we discern, or I guess some of the questions that we like to bring forth to our clients and potential customers about their
Sure.
ownership?
Oh, yeah, that's a hefty question, and I work in very similar spaces, so I empathize. I think that this is an area where technology is outpacing our approach, and so there needs to be an upgrade to a lot of like contract litigation to reflect the complexities of data usage and AI, and I think that's something that we've all experienced, is that as technology increases, the law often is slow to catch up. But if it's a good faith relationship, I would say that negotiating more than just data ownership. So, for instance, with machine learning, I've negotiated a contract where I'm able to use the data to train the algorithm. The data remains my client's, the algorithm remains the firm's.
Gotcha.
And so it's an approach. So you can, for intellectual property, you can retain the IP rights to your approach, or you can, have limited IP contracts, or very detailed non-disclosure agreements. And so I think the question for coming at it from a consulting perspective, but really for any business, is what do you want to get out of it? Do you want the data itself? Because a lot of times in data science, like the data is great, but it's actually the analytics, or it's the approach. And that's what you want to patent, and that's what you want to sell. Because then you can give it to any client, they can insert whatever data they want, and they get still the same results. And so I would almost encourage you to not be really concerned about who owns the data, and focus more on the approach, because that's the tougher thing. And that's actually the really valuable thing that you can sell and you can use again and again.
Yeah, pretty good.